Welcome to the deep dive. Today we're heading straight into the core of Palo Alto Network's firewalls.
hmm
These are, the sophisticated security powerhouses that form the backbone of defense for so many organizations out there.
They really are critical pieces of infrastructure.
Right. And if you're serious about understanding how these operate, maybe you're prepping for a technical chat, aiming for a real command of network security, or you're just fascinated by the tech protecting us well. Surface level stuff just isn't enough.
Definitely not.
So this deep dive is designed to really unpack their inner workings, give you that essential understanding.
Exactly. And what we've been doing is looking at some pretty advanced interview questions, the kind they ask experienced firewall pros.
Ah, okay. So these aren't your basic "what is a firewall" questions.
Not at all. They really dig into the fundamental mechanisms, what actually makes these systems tick.
Right. So our mission today is to pull out that critical knowledge, really get under the hood of how PAN firewalls function.
Yeah, clarify the key processes, the components.
And give you insights that hopefully go well beyond just a basic overview. Okay, let's get started. Where should we begin? At the heart of the system.
Let's do that. Let's start with what you could pretty much call the central nervous system of a Palo Alto firewall, the PANCOM daemon.
PANCOM. Okay, sounds
So-
important. What's its main job?
It is vital. Think of it like the internal communication hub inside PAN-OS. Its main role is basically facilitating the exchange of data
Okay,
and making sure there's coordination between all the other key daemons running on the box.
so connects everything together.
Precisely. PANCOM is the linchpin. If it fails, you've got major problems. It can cripple communication between management and, well, the part actually enforcing things.
Okay, so who are these other key players it's talking to?
Well, you've got daemons like MGMTSRVR, that's the management server. Handles the GUI, the CLI, API access.
Right, the user interface stuff.
Exactly.
Mhm.
Then there's DevServVR, the device server. That one handles config management, pushing policy down to the data plane.
The data plane being the part that actually processes the traffic.
Yes, exactly. And PANTask is that main data plane process. It's responsible for the actual traffic forwarding.
Gotcha.
And then there's UserID, the user ID daemon. Does what it sounds like, manages user identification, mapping users to IPs.
Okay, so all these different parts need to talk, and PANCOM is the operator connecting the calls.
That's a good way to put it, like a central dispatcher or maybe a conductor, making sure the orchestra plays in sync.
Can you give us a concrete example? Like if I make a change in the GUI.
Sure. So you make a config change via the web interface, right? That hits MGMTSRVR.
Okay.
Now, for that change to actually do something to affect traffic, MGMTSRVR needs to tell DesRVR. And it does that using PANCOM. It sends the config info across.
Makes sense.
Or another example, say the firewall learns a new user-to-IP mapping from Active Directory via the UserID daemon.
Right.
UserID then uses PANCOM to broadcast that update. So the data plane knows, traffic from this IP is actually Bob from accounting and can apply the right policy.
Okay, this is where it gets really interesting. What happens if PANCOM itself runs into trouble? Or just stops? Sounds like things could grind to a halt.
Oh, absolutely. That's a very sharp observation. If PANCOM fails, that communication link between the management side and the data plane is essentially severed.
And how would you notice that?
Well, you might see the GUI or the CLI just become unresponsive. It might freeze up on you.
Okay, annoying, but maybe not critical.
But critically, config changes you think you're making on the management plane might not actually get pushed down to the data plane.
Oh, so your firewall isn't actually enforcing the rules you just set up.
Exactly. Your intended security posture isn't live on the network traffic. That's a serious issue.
Yeah, that sounds pretty bad. Is there a quick way to check if PANCOM is okay and maybe nudge it if it's not?
Yeah, there are a couple of basic things. You can run show system software status in the CLI. That shows the status of all the key processes, including PANCOM. And if you see it's not running, you can try restarting just that process with debug software restart process PANCOM. Often clears up temporary glitches.
Okay, good to know. So PANCOM is like that central dispatcher, maybe air traffic control for everything happening inside the firewall. Makes sense.
Yep.
So with that internal communication sort of mapped out, let's follow the action. What happens when a network packet actually arrives at one of these firewalls? What's its journey like?
Right, the life of a packet. It's quite a trip, actually. Happens in stages, sequentially. It starts, naturally, with ingress. Packet hits a physical interface.
Okay, step one, arrival.
And right away, the firewall does some basic layer 2 checks, like is the CRC okay? Is the framing right? Basic sanity checks.
First up, quality control.
Yeah.
Got it. If it passes.
Then the firewall needs to figure out the zone and interface. Based on which physical port the packet came in on, it assigns a source zone.
Okay, like this came from the trust zone or this came from untrust.
Yeah, exactly. And then based on the destination IP and its routing table, it figures out the egress interface and the destination zone. So where it came from and where it's headed, network-wise.
Right, like sorting mail by origin and destination zip codes within the building. What's next?
After zoning, it does a session lookup. It checks, is this packet part of a conversation I already know about?
An existing session, you mean?
Precisely. If yes, great. It applies the policies already associated with that session faster.
And if it's totally new, first packet of a flow.
If it's brand new, doesn't match anything existing, then the firewall has to create a new session entry in its state table. You obviously don't want to reevaluate rules for every single packet in a long download, right?
No, that would be incredibly slow. Makes perfect sense. So for these new sessions, what's the next gate they have to pass?
For new sessions, it's policy lookup. This is where your security rules, the ones you configured, actually get evaluated.
Okay, the core firewalling part.
Right. The firewall looks hard at the packet's 5-tuple, that's source IP, destination IP, source port, destination port, and protocol, plus the zones we just talked about, and maybe user ID info.
The 5-tuple is key for writing rules, isn't it?
Absolutely fundamental. So the firewall takes this tuple and compares it against your security rule base, top to bottom.
Top to bottom. That order is critical then.
Hugely critical. It stops at the first rule that matches.
So a badly placed allow any rule could short circuit everything above
It
it.
absolutely could. Once it finds a match, the action in that rule, usually allow or deny, is determined. But wait, there's more.
Oh, what else?
Before it actually lets the packet go, if allowed, there's potentially NAT processing,
Yeah.
network address translation.
Changing IP addresses or ports.
Exactly. If you've got NAT rules configured, source NAT, destination NAT, whatever this is where they kick in, the addresses might get translated before the next steps.
Okay, so NAT happens before the final policy decision based on the potentially translated addresses.
Actually, let me clarify that sequence slightly. It's a common point of confusion. The initial policy lookup happens first to see if the session is even allowed between the original zones. If it is allowed, then NAT policy lookup happens to see if addresses need translation. Then the security policy is checked again, potentially against the post-NAT attributes if needed, especially for things like security profiles. But the key is, NAT is evaluated in conjunction with the security policy processing, not strictly before the initial allowed any check.
Okay, thanks for clarifying that nuance.
Yeah.
So policy check, NAT check, maybe more checks. What about the really clever stuff Palo Alto is known for? The application identification.
Right, that comes next. App ID and Content ID. App ID, the application identification engine, jumps in to figure out what application is really generating this traffic.
Not just looking at the port number.
Definitely not just the port. It might need to inspect, up to maybe 8 initial packets to really nail down the application.
Wow, okay, so it watches the conversation start.
Exactly. Once the app is identified, say, it figures out this isn't just generic web traffic, it's specifically Facebook chat. Then Content ID can take over.
And Content ID does the threat scanning.
Yes. Based on the identified app, it scans for viruses, spyware, exploits, malicious files, all that nasty stuff.
So App ID tells Content ID what to look for, essentially.
In a way, yes. It provides crucial context.
What if the traffic's encrypted? How does it inspect inside HTTPS, for example?
Excellent point. If SSL decryption is configured and enabled for this traffic.
Which we'll talk more about later, I assume.
We will. But if it is, this is the stage where the firewall decrypts the traffic. It acts as a man in the middle, basically.
Okay, opens it up.
Opens it up, allows App ID and Content ID to do their inspection on the clear text content, and then re-encrypts it before sending it on. Obviously needs careful setup.
Right. Trust and certificates involved there. After all that inspection, what happens?
Assuming the session is allowed and established, the firewall generates logs, records the details, who, what, where, when was it allowed, what app was it, any threats found.
Crucial for visibility and forensics.
Absolutely. And then finally, the packet reaches the egress stage. It gets forwarded out the correct interface based on the routing table toward its final destination.
Phew. Quite the gauntlet. From hitting the wire, getting zoned, session checked, policy applied, maybe natted, definitely app ID'd and content scanned, maybe decrypted, then logged and finally sent on its way.
It is. Like that package going through the postal system analogy, you used lots of checkpoints. Address verification, customs inspection, content screening, final delivery truck.
Yeah, that works really well. Okay, let's zoom back in on one of those really important checkpoints, App ID. How exactly does it figure out the application? You said it's not just ports.
Right. App ID is, well, it's pretty sophisticated. It's a cornerstone of PAN-OS. It uses multiple techniques together.
Okay, like,
It uses application signatures. These are unique patterns, like fingerprints, known to be associated with specific apps or protocols.
so pattern matching.
Yep. It also does protocol decoding. It actually understands the language of many protocols, analyzing the back-and-forth communication to see if it matches, say, the structure of an SMB file transfer or an SIP call setup.
So it speaks the protocols.
To a large extent, yes.
Yeah.
Then there are heuristics. It looks for characteristic behaviors, like does this traffic flow behave like BitTorrent, even if it's trying to hide on a weird port?
Behavioral analysis.
Yeah.
Clever.
And as we mentioned, if SSL decryption is on, it can obviously use the decrypted content itself to identify the application with much higher certainty.
So it's a multi-layered approach, signatures, protocol smarts, behavior, and potentially looking inside encryption. It doesn't just rely on one thing.
Exactly. It starts often with a guess based on port and protocol. Traffic on port 80. Okay, initially tag it as web browsing.
Traditional way.
Right. But then as it sees those first few packets, maybe packets 2, 3, 4, it looks at the actual payload data, the signatures, the protocol structure.
And it might change its mind.
Precisely. It might say, hold on, this isn't just generic web browsing. Based on this HTTP header and this payload pattern, this is actually Facebook-based. So it refines the classification.
That's really interesting. What if the app changes mid-session? People do multiple things in one long web session, right?
Good question. That happens all the time. Maybe you start browsing a news site, web browsing, then click a link to watch an embedded video, YouTube-based, then open a chat window, Facebook chat.
How does the firewall handle that shift?
This is where App ID's dynamic nature is key. When it detects that the application within the existing session has changed.
Like from web browsing to YouTube base.
Exactly. It updates the app ID associated with that session in real time. And critically, it then reevaluates the security policy against that new app ID.
Wow. Okay, so it checks the rules again midstream.
It does. If your policy allows the new application, YouTube base in this case, the session just continues seamlessly, no interruption.
But what if the new app isn't allowed? Maybe I block YouTube.
Then if the reevaluation against the policy finds that YouTube base is denied, the firewall will typically reset the session, tear it down.
So it dynamically enforces policy even if the application identity shifts mid-conversation.
That's the power of it. It ensures security isn't based just on the first guess, but on what's actually happening throughout the life of the session. It's not just looking at the envelope's address, it's continuously aware of the content type.
That really drives home the difference from older firewalls. It's truly application aware, not just port aware.
Absolutely. Now, to understand how all this processing the packet journey, the app ID happens efficiently without, melting the CPU, we need to talk about the architecture, specifically the management plane versus the data plane.
Yes, the classic separation. I've heard those terms. Can we break down what each one does and, maybe more importantly, why they're separate?
Let's do it. Think of the management plane as the control center, the headquarters.
Okay.
Its job is all the administrative stuff, configuration, you interacting with the GUI or CLI, that's management plane. Running those daemons we talked about earlier, like MGM, TSRVR, DevZeroUR, UserID, logging, reporting generation, that all happens here.
So setting things up, monitoring, managing the device itself, less real-time traffic processing.
Generally, yes. It's less CPU intensive in terms of packet per second processing, though generating a massive report could certainly spike its CPU usage.
Okay, that's the management plane, the brains. What about the data plane?
The data plane is the engine room, the factory floor, it's the muscle. Its job is one thing, primarily. Forwarding traffic as fast as possible.
This is where Pantask lives.
Exactly. Pantask flow, DPE, these processes run here. This is where session setup actually happens for the traffic, where NAT occurs, where app ID and content ID inspection take place on the packets themselves.
So all the heavy lifting for the actual network flow.
Precisely. It's highly performance critical. It's built for speed and efficiency in handling potentially millions of packets per second.
Okay, so one manages, one processes traffic. Why is this separation so important? What's the big benefit?
Resilience and performance. Because the data plane is dedicated to just processing traffic, it can run full tilt without being slowed down by management tasks.
Ah, so if I'm running a huge report in the GUI, which taxes the management plane.
Exactly. Even if the management plane CPU spikes or the log viewer temporarily freezes up.
The data plane just keeps chugging along, forwarding packets.
Correct. Traffic flow continues uninterrupted. Your network doesn't grind to a halt just because you're doing administrative work. This separation is absolutely key to Palo Alto's stability and performance under load.
That makes a ton of sense. It's like having the company's management plane, separate from the production line, data plane. Problems in the office don't stop the factory.
That's a perfect analogy.
All right. Now, another area that often feels like navigating a maze is network address translation, or NAT. PAN-OS supports different flavors, right? Can we break those down?
You bet. NAT is essential, but yeah, the different types can be confusing. Let's walk through them. The most common one you'll see is probably source NAT.
That's for outbound traffic. Internal users going to the internet.
Typically, yes. It changes the source IP address. Usually it replaces the private internal IP of a user's machine with the public IP address of the firewall's external interface. So multiple internal users can share one public IP to get online.
Got it. Hides the internal structure, allows use of private IPs. What about traffic coming in?
That's where destination NAT comes in. It changes the destination IP address of incoming traffic.
Like if I'm hosting a web server internally.
Exactly. Someone on the internet tries to connect to your public web server IP. The firewall receives that, sees a destination NAT rule, and changes the destination IP to the private IP address of your actual web server on the internal network. It forwards the request inwards, used for publishing internal services.
Okay, makes sense. Source NAT for outbound, destination NAT for inbound. Any others?
Yep. There's static NAT. This is a fixed one-to-one mapping. This public IP always maps to this private IP, and vice versa.
When would you use that instead of destination NAT?
Often used for servers, maybe in a DMZ, that need a dedicated public IP address that doesn't change. It ensures both inbound connections to that public IP reach the server, and outbound connections from that server appear to come from that same public IP. Consistent identity.
Okay, one-to-one permanent mapping. What if I have lots of users going out, but maybe only a few public IPs?
Right. If simple source NAT using just the firewall's interface IP isn't enough, you can use dynamic IP NAT. Here, you define a pool of public IP addresses. As internal users initiate outbound sessions, the firewall grabs an available IP from the pool and assigns it to that session.
So it shares a pool of addresses among many users.
Yes. And an even more common variation, especially for scaling, is dynamic IP and port NAT, usually just called PAT, port address translation.
Ah, PAT. I've heard of that. How's it different?
With PAT, multiple internal users can share the same single public IP address. The firewall differentiates their sessions by assigning unique source port numbers to each outbound connection. It translates both the source IP and the source port. Hugely scalable. Most home routers do this.
Right, that's how thousands of users in an office can share one main internet IP. Very efficient. Anything else in the NAT world?
Just one more main type to mention. Bidirectional NAT. This combines elements of source and destination NAT, essentially translating both source and destination addresses in a single rule. It's less common, used in more complex scenarios, maybe dealing with overlapping IP address spaces between merging networks or specific partner connections.
Okay, that sounds a bit more niche. Now, you mentioned the interaction with policy earlier. Can you reiterate that critical point about when NAT rules are evaluated?
Absolutely crucial. Remember the sequence. Initial security policy lookup checks if the connection is allowed between zones based on original IPs. If allowed, then NAT policy is checked. If a NAT rule matches and translation occurs, the packet now has new translated IP port info. Then, security profiles, content ID, etc., and potentially further policy checks are applied based on the post-NAT attributes and the identified application.
So the security engine sees the traffic after any address translation has happened.
Correct. The final enforcement and inspection happen on the packet as it will actually appear on the network post-translation. You must factor this into how you write your security rules. If you NAT an internal server's IP to a public IP, your security rule needs to allow traffic to that public IP in the relevant zone, not the original private IP.
Got it. Build security rules based on the final address after NAT does its thing. It's like the firewall puts disguises NAT on its inhabitants before the security guard's policy inspect them.
That's a decent way to think about it, yeah. Manage the identity first, then check permissions.
Okay, that clarifies NAT quite a bit. Now let's talk about resilience. Downtime is a killer. How does Palo Alto handle high availability, keeping things online?
Right. Keeping the network up is paramount. PAN-OS has robust high availability or HA features. It primarily supports two modes, active-passive and active-active.
Okay, active-passive sounds like one is working, one is waiting.
That's the basic idea. In active-passive, you have two firewalls, but only one. The active one is actually processing traffic at any given moment. The other one, the passive unit, is sitting there in a standby state.
Just waiting. What's it doing while waiting?
It's not idle. It's constantly getting updates from the active unit. They exchange heartbeat signals over a dedicated control link, the HA1 link, to check if the other is alive and well. They also exchange hello messages.
Okay, constantly checking pulses.
And crucially, the active unit synchronizes its state information over to the passive unit. This includes the configuration, of course, but also real-time stuff like the current session table, NAT translations, routing information, usually over a separate data link, the HA2 link.
So the backup knows exactly what the primary was doing.
Yes. So if the active unit fails, the passive unit already has all the necessary information to take over almost instantly and start processing traffic with minimal disruption. It assumes the active unit's IP addresses and roles.
Okay, that sounds pretty seamless. What actually causes that failover to happen?
Several things can trigger it. Link monitoring is common. If a critical interface on the active unit goes down, like the main internet link, it might trigger failover. Path monitoring is similar, checking reachability to a downstream IP address.
So network connectivity issues.
Right. Or, obviously, a device failure, hardware problem, power loss, critical software process crashing on the active unit. The heartbeat will stop, and the passive unit takes over. Even failure of the HA links themselves can trigger failover under certain configs, as the units can't be sure of each other's state. And you can also configure monitored IP addresses if the active unit can no longer ping a critical internal server, for instance. It might mean there's a bigger problem, so it fails over.
Lots of triggers. Now, you also mentioned active-active. How does that differ? Sounds like both are working.
In active-active, specifically Layer 3 active-active, yes, both firewalls are actively processing traffic simultaneously. It's more complex.
How does that work without conflicts?
It uses things like floating IT addresses that can move between devices and clever logic to determine which firewall owns a particular session and which one should handle the forwarding. It can potentially offer higher aggregate throughput because you have two engines working.
But more complex, you said.
Generally, yes. Configuration is more involved. Troubleshooting can be trickier. You have to think about session symmetry, making sure traffic for one session goes through the same firewall in both directions. Active-passive is often simpler and sufficient for many environments.
Makes sense. Simpler is often better if it meets the need. Any best practices for setting up HA?
Definitely. Always use dedicated physical interfaces for your HA1 control and HA2 data synchronization links. Don't share them with regular management or data traffic if you can avoid it. Physical separation is key for resilience.
Keep the HA communication isolated.
Exactly. And think carefully about preemption. Preemption means that if the original active unit fails and then later recovers, should it automatically take back control?
Seems like it should.
Maybe, but enabling preemption can sometimes cause flapping if the unit is unstable, failing over back and forth. Disabling preemption means the unit that took over stays active until you manually intervene. It's often more stable but requires admin action to revert. It needs careful consideration based on your environment.
Right. Stability versus automatic recovery. Trade-offs. It's clear there's a lot of engineering just to keep things running smoothly, even if hardware hiccups.
Absolutely. Uptime is king.
Okay, shifting gears again. Encryption. It's everywhere, which is good for privacy but bad for security inspection. How does Palo Alto let you peek inside that SSL TLS traffic, SSL decryption?
Right. SSL decryption is a very powerful but also sensitive capability. It allows the firewall to inspect encrypted traffic, primarily HTTPS, for threats hidden inside.
How does it work? Magic.
Hey, not quite magic, more like a carefully orchestrated interception. There are two main modes, SSL, forward proxy, and SSL inbound inspection.
Okay, forward proxy. That sounds like it's for traffic going out from my network. Users browsing the web.
Exactly. SSL forward proxy decrypts outbound SSL TLS connections initiated by your internal users going to external sites.
So, user tries to go to https.mybank.com.
The firewall intercepts that connection attempt. Instead of the user talking directly to the bank server, the firewall does two things. It establishes its own secure SSL connection to the bank's server.
Okay, firewall talks to bank.
And simultaneously, it pretends to be the bank's server and establishes a different SSL connection back to the user's browser.
Whoa, Okay, man in the middle.
Precisely. It sits in the middle, it decrypts the traffic coming from the bank, inspects it using App ID and Content ID.
Looks for malware, bad stuff.
Right. Then, if it's clean, it re-encrypts the traffic using the certificate it presented to the user and sends it to the user's browser. The user thinks they have a secure connection to the bank, but the firewall is mediating.
But wouldn't the user's browsers scream about the certificate not matching the bank's actual certificate?
Ah, that's the crucial prerequisite. For forward proxy to work transparently, the firewall generates certificates on the fly for the site's users visit. But it signs these fake certificates using its own special certificate authority, CA certificate. You must install this firewall CA certificate as a trusted root CA on all your internal client machines, usually via group policy or MDM.
So the clients are configured to trust certificates signed by the firewall.
Exactly. Then they don't get browser errors. Without that trust established, decryption breaks the user experience.
Okay, that's forward proxy for outbound. What about SSL inbound inspection? Traffic coming into my network.
This is for decrypting traffic destined for your own internal servers that you publish securely, like your company's HTTPS website.
How does that work? Does the firewall also generate certs?
No, in this case, for the firewall to decrypt traffic coming to your server, it needs the server's actual private key.
Oh, wow. Okay, so I have to load my web server's private key onto the firewall.
Yes. Securely, of course. When an external user connects to your public HTTPS site, the firewall intercepts it. Using the server's private key that you loaded, it decrypts the incoming traffic.
Inspects it.
Inspects it for threats, like attacks targeting your web server. If clean, it re-encrypts it using the server's actual certificate and forwards the now clean traffic to the internal web server.
So it protects your internal servers by inspecting incoming encrypted traffic, but requires access to the server's private key.
Correct. Both modes are essentially man-in-the-middle, allowing inspection, but they operate differently and have different prerequisites.
Are there limitations, times when decryption just won't work or maybe shouldn't be used?
Yes, definitely. Some applications use certificate pinning. They hard-code the expected certificate for the server they connect to. If the firewall tries to slip in its own forward proxy certificate, the application will reject the connection. Decryption breaks these apps.
Okay, pin certs are a problem.
Perfect forward secrecy, PFS, can also be a challenge, particularly for passive out-of-band decryption, though modern firewalls handle common PFS cipher suites okay for active decryption, like forward proxy. Also, if a connection uses a really old or obscure cipher suite that the firewall doesn't support, it won't be able to decrypt it.
And some traffic you might specifically exclude from decryption for privacy or legal reasons, right? Like financial healthcare sites.
Absolutely. Most organizations create exclusion lists for sensitive categories like that. It's a balancing act, security, visibility versus privacy and functionality. Decryption gives the firewall the ability to see inside encrypted tunnels, but you have to acknowledge its limits and use it wisely.
Really clear breakdown, thanks. Okay, one last feature on our deep dive list. Application override. Sounds like a bypass switch.
It kind of is, yeah. Application override is a way to tell the firewall, hey, for traffic matching these specific criteria, don't try to use App ID to figure out what it is. Just assume it's this application that I'm telling you it is.
Why would you ever want to stop App ID from working? Isn't that the whole point?
It seems counterintuitive, right? And you're right, it bypasses a core strength, so it should be used very, very sparingly. But there are a few potential use cases.
Like what?
Maybe you have a completely custom in-house application that uses a standard port, like TCP 5000, but App ID doesn't recognize it, or worse, misidentifies it as something else, causing policy issues.
Okay, proprietary stuff App ID doesn't know.
Right. Or maybe in some very specific low latency environments, like maybe some industrial control systems or specialized financial feeds, the tiny overhead of App ID inspection might be deemed unacceptable, and you accept the risk, though that's a big risk.
Seems risky, yeah.
Another case, perhaps less ideal, is if App ID is consistently misidentifying some legitimate traffic, and you need a temporary workaround while you work with Palo Alto support or update signatures to fix the real identification problem. An override can keep things flowing in the meantime.
So it's mainly for exceptions or temporary fixes when App ID gets confused or isn't suitable for some niche traffic. How do you set it up?
You define the traffic very specifically, usually by destination port, destination IP address, or subnet, and the protocol, TCP/UDP.
Okay, very precise targeting.
Yes. And then you assign a custom App ID name to it, like my override. When the firewall sees traffic perfectly matching that port, IP, and protocol combination.
It just slaps the my override label on it.
Exactly. It skips the normal app ID signature, decoder, and heuristic checks. It just tags it as you defined. And here's the kicker. Because it skipped app ID, it also skips most of the content ID inspection, threat scanning, file blocking that relies on knowing the true application context.
Ah, there's the big risk. You lose the threat inspection for that traffic.
Pretty much. The traffic is treated generically based on the override rule. You lose that deep application-specific security analysis. That's why it's potentially dangerous. You're essentially punching a hole in your app ID visibility and protection for that specific flow.
So if you override something on port 80, you won't get checks for web exploits or malware downloads within that specific overridden session.
Generally, no, because the firewall no longer definitively knows it's web traffic. It just knows it's my override. So it must be used only when absolutely necessary with a full understanding of the trade-offs. It's a powerful tool, but like a manual override on safety equipment use with extreme caution.
Got it. A tool of last resort, not first instinct. Well, this has been incredibly insightful. We've really covered a lot of ground today.
We have, from PANCOM handling internal messaging
To the whole journey a packet takes, getting inspected and identified.
the cleverness of app ID figuring out what's really running.
The critical split between the management and data planes for performance.
All those different flavors of NAT.
Keeping things online with high availability.
Peeking inside encryption with SSL decryption.
And finally, that application override bypass switch.
Yeah, understanding these pieces really gives you a much deeper appreciation for how sophisticated these firewalls are. They're way beyond simple port blockers. They're intelligent systems trying to understand and secure complex application flows.
Absolutely. And it really makes you think, doesn't it? Considering all the complexity we've just unpacked inside this one box, what other layers of security might be working alongside it to protect our digital world? And, maybe more importantly, how do all these different systems, firewalls, endpoint security, cloud protection, threat intel feeds, actually coordinate and work together to create that strong layered defense we rely on?
That collaboration piece is definitely something to chew on. How do they form a cohesive whole?
Exactly. Something to ponder until our next deep dive. Thanks for joining us today.